Hello, so here we're back again, and now we're looking at the application of alternating series estimation theorem. So I abbreviated it ASET with integration. So we'll see how we can apply this theorem that we saw in the previous video to integration. So whenever we have a task where we have to approximate or estimate a specific integral, accurate to 6 decimal places, what we do is we first look at the function or the integrand that we have. So let's call that f of x. So f of x is equal to 1 over 1 plus x to the 5th power. Now what we're going to try to do is to find the power series representation of this function. So how do we do that? Well, we first recall that the power series representation for 1 over 1 minus x is equal to the summation of x to the n as n goes from 0 to infinity. Correct? And this is, of course, only convergent when the absolute value of x is less than 1. Then we know that if you do 1 plus x, well, that's the same thing as 1 over 1 minus negative x. So we're using this previous series as a template to find my other power series representation for this function 1 plus x. In this case, it's going to be the -1 will be part of the raised to the nth power and have x to the n as well. Again, we've seen things like this already. So now when we have 1 plus x to the 5th power, it's really just the same thing as this series, except that now I'm going to have n equals 0 to infinity, -1 to the n for x to the 5n. So I can represent this power series representation of this function as the summation as n goes from 0 to infinity of -1 to the n x to the 5n. So the power series becomes very important and very applicable, useful, when we want to integrate functions for which finding the antiderivative is very difficult. Because now I have a way to represent a function, 1 over 1 plus x to the 5, as a sum of power functions. And we can find just a few of the first few terms. So when n equals 0, we have 1 as our first term. When n equals 1, we have this alternating thing happening, and we have x to the 5th power. And then we have when n equals 2, x to the 10th power, and so on, right? X to the 15th power, and plus or minus, right? So what we're going to do now is integrate. From 0 to 0.2, we're integrating this function, which I can find the integral of if I represent it as its power series representation as the sum that we just saw above. From 0 to 0.2. And equivalently, so let me put this down here so there's no confusion. Equivalently, I can represent this as the integral from 0 to 0.2 of the summation of n equals 0 to infinity of -1 to the n x to the 5n dx. So I'm going to do this side by side. So do you see all these these integrals? They're all identical. Here I have the function the way it was first defined for us, this definite integral. This second part of the equation, this function now is represented as its power series representation, but of course I use these dots because I can't introduce an infinite sum. And then this third part of the equation is this sum, but represented in shorthand notation with this summation symbol. These are all identical, right? So it's good to see this, the side-by-side view of the integration, just to see how they're connected, because now I can find the antiderivative of each of these terms quite simply. So this would be x minus x to the 6 over 6 plus x to the 11th over 11 minus x to the 16 over 16 plus ... right? And I can also rewrite this as the summation (-1 to the n), the integral from 0 to 0.2. Oh, and I forgot one thing. I'm assuming that I am finding the antiderivative of every term in this infinite sum, which I have in the bottom, and then I'm evaluating it. I'm evaluating this using the fundamental theorem of calculus at the upper bound of 0.2 and the lower bound of 0. Okay, now this is equivalent for me just to integrate the series as so. And when I find the antiderivative of x to the 5n, I use the antiderivative rule of adding 1 to the exponent and then dividing by that same exponent. And of course, I'm also evaluating this at 0.2 and at 0, right? So if you notice, this expression here and this expression here are identical. They are the same. Now, when I plug in 0.2 everywhere I see x, when I plug in 0.2 everywhere I see x, I get an alternating series. I get 0.2 minus 0.2 to the 6th over 6 plus 0.2 to the 11th over 11 minus 0.2 to the 16th over 16 plus ... which is the same thing as saying the summation n equals 0 to infinity of (-1 to the n, 0.2 to the 5n plus 1 all over 5n plus 1. Now, I also have to plug in the 0 as the 0 value for x, right? The 0 value for x. But if you're plugging in 0 into all these x's, you get 0. So evaluating their antiderivative at 0 just gives a 0, so I don't have to worry about it. So now this goes back to where we talked about the alternating series estimation theorem. Remember, we're trying to approximate the sum. We know this converges because it follows that the alternating series has a decreasing sequence whose limit as n goes to infinity goes to 0. So this converges. Now, what does it converge to? I don't know exactly, but I can approximate it. So this converges to some value s. Now, I want to approximate this limit to 6 decimal places. So then how do I interpret this? It means that whatever the remainder is, it should be less than 10 to the -7th, or in other words, 0.00000001. Remember, I want the first 6 decimal places for the error to be 0. That's what this is saying. I want and remember what R of n means. R of n means the actual value of the limit of the sum minus the partial sum, that difference between the approximate value with the actual value. I want that difference to be less than 10 to the -7 or 0.000001, which indicates that the first 6 decimal places are accurate. They're the same. The first 6 decimal places for Sn and the first 6 decimal places for S are accurate for the first 6 decimal places. So how do we determine how many terms we need? That's really what the crux of the problem is. How many terms do I need to approximate it enough so that the first 6 decimal places are indeed the same decimal places as the actual limit? So that's where I have to compare or compute the values of b sub 1, b sub 2, b sub 3, b sub 4, and so on. So let's do b sub 1. Well, b sub 1 is very simple, is 0.2. And then we go to b sub 2, 0.2 to the 6th power over 6. So we can compute that. And I'm going to use my calculator for that. So I'm going to compute that. So I got 0.2, and I raised it to the 6th power. and I divide that by 6. And I get 0.0000. That's 4 decimal places with 106. So you see the first 4 decimal places here will be the same. Well, let me go back. Well, okay, I'm going to show you what I wrote afterwards. So B3 is going to be 0.2 to the 11th power. Let me just see. 0.2 to the 11th power over 11. I'm going to compute the second or the third term. So second, enter, and I get 0.2 raised to the 11th power over 11. And I get 0.0000000. I get 8 zeros. 1 8. So let me just switch back. So these are my terms. And I want it to be rounded to the nearest 6 decimal places. If I stop at B2, only the first 4 decimal places will be accurate. If I stop at B3, the first, let's see, 1, 2, 3, 8 decimal places will be accurate. This is only the first 4 decimal places. And I want the first 6 decimal places to be accurate. So it must mean that B3 is going to be my upper bound because B2 is too small. So if B3 is the upper bound to my if B3 is the upper limit to my remainder, then that means that I must be finding the partial sum with 2 terms. Remember recall the alternating series estimation theorem states that the remainder is equal to the difference between the actual limit or the actual sum of the series minus the partial sum of the series. It's less than or equal to the n+1 term in the sequence. So if I just recognize that the third term in the sequence for the series, if that's going to be the upper bound that I need, that means that I must have computed the remainder between the partial sum and the S2, which is the partial sum with its first 2 terms. So this indicates that S is approximately S2 for the, and S2 is accurate with, or as accurate within, for the first for the first 6 decimal places. So then what's S of 2? Well, S of 2 is B sub 1 minus B sub 2. What's B sub 1? It's 0.2. What's B sub 2? Is 0.2 to the 6 over 6. So then when you put it in your calculator, and I compute, so I'm going to compute 0.2, and then I'm subtract the fraction 0.2 to the 6 and put that over 6. And what I get is 0.1998933. Dot. So this is approximately the actual sum. So this is the approximate again, the approximate sum. And this is the actual sum. Under the alternating series estimation theorem, I know that my approximate sum of the first two terms in the series, if I add those two numbers together, I get a value that is quite accurate. I think I'm missing another 9. Sorry about that. So I know I'm going to be accurate within the first 1, 2, 3, 4, 5, 6. These first 6 decimal places are going to be exactly what the actual sum will be for the first 6. The other numbers after that are just going to be approximations. It's going to be approximately off. It's going to be not exactly the same as the actual sum. So now I'm able to compute the value of this integral using a way to approximate the integral by applying the power series of the function, integrating it using the alternating series estimation theorem to bound the remainder, so that now I can use with precisely what the precision I'm expected to have, which is the first 6 decimal places, being accurate. And that's how we compute it.